Hello, so today we're going to be looking at ionization energy, and ionization energy is a measure of the energy required to completely remove an electron from an atom of an element. So this follows on from our lesson on mass spectroscopy, where we were looking at the second step of mass spectroscopy, which was ionization. And remember, ionization is when a high energy beam knocks off an electron from a gaseous atom. And this keyword here, gaseous, is important in the next slide. So ionization energy is the energy of an electron when removed. Take away the energy of an electron when in the orbital. So let's look at our first definition. Our first ionization energy is the energy required to remove 1 mole of the most loosely held electrons from 1 mole of gaseous atoms to produce 1 mole of gaseous ions, each with a charge of +1. So because it is the first ionization energy, we're only removing 1 electron. We're only going to be forming 1 plus ions. That's why the definition specifically says with a charge of +1. The most important things here are looking at those 3 bold highlighted parts of our definition. The first one being energy required. So because this is the definition for first ionization energy, we need to mention obviously energy is required to remove 1 mole of electron. The 1 mole itself is important. Without writing the word 1 mole, we'd lose a mark in our exam for the definition. And remember, it has to be gaseous atoms, as I mentioned previously, our mass spectrometer, before we reach the ionization chamber, where the electron beam knocks off an electron. We have to vaporize our sample. So our first step in mass spectrometry is vaporization, which causes our atoms to become gaseous first. So again, without the term gaseous atoms, we lose a mark. So these words that I've highlighted in bold are really important when you're talking about a definition for first ionization energy, because these are the words which will guarantee you marks in your definition. So successive ionization energies in any given element, you can have more than one ionization energy, provided you have more than 1 electron that could possibly be removed. So for example, in carbon we have 6 electrons, so therefore 6 electrons can be removed. In nitrogen we have 7 electrons, so potentially you're going to have seven successive ionization energies, because 7 electrons can be removed. In sodium, for example, you can have 11 ionization energies because you have 11 electrons, so therefore theoretically you can have 11 electrons being removed. So let's take any element, for example element X. As you can see here, you're knocking off an electron from X to make it into an ion. So X goes to X plus because you've removed an electron, plus E minus, referring to the electron that's been removed. As you can see, the state symbols are both gaseous because we've gone through the process of vaporization, where our atoms have become gaseous first, and then only then can they get ionized. In the second ionization energy reaction, or the equation we use to represent that, we have X plus going to X2 plus E minus. It's very important to note here that instead of going from X to X2 plus 2E minus, we're going straight from X plus, which is our first ion from our first ionization energy, and then we're converting that to X2 plus by knocking off 1 electron. So each ionization energy equation, there should only be 1 electron. So X plus goes to X2 plus E minus, again in the gaseous state. So our third ionization energy, for example, would be X2 plus goes to X3 plus E minus, again both in the gaseous state. So we can't just jump straight from our normal atom to a 2 plus or normal atom to a 3 plus. We have to go through these stages of different ionization energies. So X goes to X plus plus E minus, X plus goes to X2 plus E minus. We can't have X going to X2 plus 2E minus, because remember that these ionization energies are successive. It happens one after another. So you can have as many successive ionization energies as there are electrons in the original atom. So for example, aluminium has 13 electrons, therefore aluminium can have 13 ionization energies. So in this example here, they've given us 4 ionization energies of aluminium. So Al goes to Al plus E minus, Al plus goes to Al2 plus E minus for the second ionization energy. Al2 plus goes to Al3 plus E minus for third ionization energy, and Al3 plus goes to Al4 plus E minus for fourth ionization energy. So as you can see, it's like a series of steps to get to Al4 plus. So our first ionization energy is 577, second ionization energy is 1820, third is 2740, and fourth is 11600, so 11600. So as you can see, as you keep knocking off electrons, as you increase our ionization energy, our energy taken for the ionization energy increases. So 577 increases to 1820, which increases to 2740, which increases to 11600. In order to form an Al3 plus ion from Al, how much energy would you need? So this is the question, and how to answer it is looking at Al going to Al3 plus. So that would require going to the third ionization energy where Al3 plus is formed. So we need to look at the first, the second, and the third ionization energy. So we look at those values because we want to work out how much energy would you need. So we have 577 for our first ionization energy, 1820 for our second ionization energy, 2740 for our third ionization energy. Add them all together, we get 5137 kilojoules per mole. So again, ionization energy is measured in kilojoules per mole. Remember, because it is per mole in our definition as well. So as you can see, when you work out energies needed for Al to form Al3 plus, for example, we have to look at the successive ionization energies, which allows us to form Al3 plus from Al. So Al going to Al plus going to Al2 plus, Al2 plus going to Al3 plus. So three separate equations there that we need to factor into account. So when we're looking at successive ionization energies, we can see some patterns. So usually with successive ionization energies, you can formulate graphs for different elements. So in an exam, they might give you a graph for a particular element. So here they're giving us a graph of sodium. On the x-axis, it shows the number of electrons removed. So obviously with sodium having 11 electrons, you have 11 numbers 0 to 11 on the x-axis at our scale, and we have ionization energy, obviously in kilojoules per mole. Here they just use joules, which is on the y-axis. The first observation here is that your ionization energies get larger as you tend to remove more electrons. So once you remove the first electron, you are left with a positive ion. So because now you're left with a positive ion, you've got more attraction between your positive nucleus and your electrons. So sometimes you might even be going down in levels. So if you knock off an electron from 3s1, you go down to 2p6. So you get shells or subshells which are closer to the nucleus, which have a greater attraction to the nucleus as well. So removing an electron from a 2 plus to a 3 plus ion is going to be progressively more and more difficult because you're trying to remove an electron from a positive ion. Okay, your observation 2, there is a big jump from the 9th to the 10th ionization energy. So the reason for this is that the last 2 electrons are in the first quantum shell. Remember, your innermost shell is the 1s orbital, so 1s2, 1s2 and 1s1. So the electron in a 1s orbital will be difficult to remove as it is closest to the nucleus. Remember, the closer the electron is to the nucleus, the less shielding there is, and the greater the attraction between the nucleus and the outer electrons. So because we have an electron 1 in a 1s orbital compared to 2s previous to that, 2s it's further away from the nucleus, and it's in the second shell, whereas 1s is closer to the nucleus because it's in the first shell. So in the 10th ionization energy, we're actually removing an electron from our 1s orbital rather than our 2s orbital. So we've decreased a shell, got rid of our 2s shell, we're left with our 1s orbital, or our energy level 1, or shell 1. And therefore it's very hard to remove anything or any electron from our first shell because it's so strongly attracted to the nucleus. So getting rid of 1s2, one electron from 1s2 is a lot more difficult than getting rid of an electron from 2s1, for example. Okay, so successive ionization energies, a big jump between 2 successive ionization energies is typical of suddenly breaking into an inner level. So that could be a change in orbital, that could be a change in subshell, that could actually even be a change in shell as well. So you can use this to work out which group of the periodic table an element is in from its successive ionization energies. So magnesium is in group 2 of the periodic table and has successive ionization energies of 736, 1450, 7740, 10,500 and 13,600. So as you can see, there's a big jump between our second and our third ionization energy. This suggests that you've actually switched subshell. In this case, because it's magnesium, you've also, if you get rid of the 3s2, you've also actually dropped down in energy level. You've gone from level 3 to level 2. Or you've removed a shell, you've gone from the third shell to the second shell. So there are a lot of derivations you can make from this little piece of information that we have, or the little amount of information that we have. So 736, 1450 going to 7740, 1450 to 7740 is a huge jump. It's just over a difference of 6,000. So 7740 then goes to 10,500, which goes to 13,600. As you increase your successive ionization energies, the more ionization energies you complete, the more difficult it is to remove an electron from the ion. So usually the big jump is quite easy to notice. So here 1450 to 7740 is a massive jump. So it's very clear that there is a change in either shell or subshell. So click on the next one. Factors affecting the energy of an electron. So which factors can affect the energy of an electron? So we have the orbital electron is in. So different electrons in different orbitals have different energies. For example, 2p has a higher energy than 2s. 3p has a higher energy than 2p or 3s. Remember that 4s has a lower energy than 3d. So orbitals do matter. Subshells also matter as well. So which shell is that subshell in? Is it obviously P subshells are going to have more energy than S subshells usually. And also shells themselves are energy levels. So 1 has a lower energy level than 2, which has a lower energy level than 3. The nuclear charge of an atom, so the number of protons in the nucleus. So the more protons there are in the nucleus, the more attraction power it has with the outer electrons. So something like magnesium, for example, has more electrons than sodium. So therefore, it will have a higher, so magnesium and sodium, it has a higher ionization energy than sodium. Because you have more protons, so magnesium has 12 protons, sodium only has 11 protons, so magnesium has a stronger attraction to its outer electrons. Repulsion due to paired electrons, remember when you talked about Hund's principle, where electrons are singly filled in a p subshell or a d subshell, for example. So because our electrons are singly filled, that minimizes repulsion in your orbitals. Once you have paired electrons in an orbital, then there could be repulsion there, which reduces attraction of the nucleus. So because they're repelling each other, that reduces the attraction of the nucleus. The number of electrons between the outer shell and the nucleus, so shielding, so the number of shells. So if it's in 3s, for example, there could be quite a bit of shielding there. If you're in 2s1, for example, it's a lot less shielding there because it's a lot closer to your nucleus. And that goes into the next point, distance of electron from nucleus. That ties in really well with shielding. So the more shielding there is, the greater the distance between the electron and the nucleus. So these are just a few points of factors affecting the energy of electrons. So you can see there's quite a few points. The last few points are very much related. So the amount of shells or the shielding that's taking place is directly linked to the distance of electrons from the nucleus. So the further those electrons are from the nucleus, the more shielding there is. So that's something that we looked at when we looked at group 1 elements, for example, uh, when we looked at it from an IGCSE perspective. As you go down the group 1 elements become more reactive because the attraction between the nucleus and the outer electrons becomes weaker and weaker as you go down the group. So therefore, it's easier to lose an electron. And the same way as you go down group 7, your group 7 elements become less reactive as you go down the group, because as you go down the group, there's more shielding between our nucleus and the outer electron, because you've got more and more shells as you go down the group. So therefore, it's harder to gain an electron because your attraction of the nucleus becomes weaker and weaker as there becomes more shielding. So I'm going to take a look at two trends when it comes to ionization energy. So there are two major trends in ionization energy in the periodic table. Number one is across a period, and number two is down a group. So as we can see from our first ionization energies across a period, so in red we've got period 2, so stretching all the way from group 1, Li, group 2, Be, group 3, boron, group 4, carbon, group 5, nitrogen, group 6 oxygen, group 7, fluorine, and group 0, the noble gases, neon. And the same for period 3, stretching all the way from Ni in group 1 to Ar in group 0. So as you can see, the general trend for our graph is that across a period, we notice that the ionization energies actually increase. So that's a very, very important point to consider. So another important point to consider is that there are two exceptions to this increase. So the first exception that you can see, hopefully, is between group 2 and group 3, so beryllium and boron, so Be and B, and Mg and aluminium. So usually the trend is the increase as you go across the period, except for these two exceptions. So let's go through the exceptions quickly. The first exception is that boron and beryllium have two different subshells. So boron is 1s2, 2s2, and 2p1. Beryllium is 1s2, 2s2. So beryllium actually ends with s2, boron ends with p1. Remember, beryllium is in group 1 and group 2, that means it must be in the s block. And because boron lies in group 3, it must be in the p block. So because our boron's outer electron is in the 2p orbital rather than the 2s of beryllium, 2p orbitals have a slightly higher energy than the 2s orbital, and it is slightly further away as well. So because it's slightly further away, our p orbital is slightly further away from the s orbital, your ionization energy would decrease. The reason being is because it's further away, there's less attraction between our nucleus and our outer electron. Also, the 2p orbital is more shielded than the 2s electron because it is actually being shielded by the s orbital. Whereas if you start with beryllium, you're only shielding with the 1s orbital because you're already in the 2s orbital. So there's not much shielding going on in beryllium, whereas boron there's more shielding going on, so that high amount of shielding would lead to reduced attraction between the nucleus and the outer electrons. The other exception to the rule is between group 5 and 6, so if you look at nitrogen, oxygen, and phosphorus and sulfur. So nitrogen, remember, is 2p3, oxygen is 2p4, and according to Hund's principle, our electrons singly fill our orbitals first in either p or f, for example. So because n is p3, your electrons singly fill each orbital in that p subshell, whereas oxygen is p4, so therefore you have the singly filled 3, but then the remaining 1 in that 4 would have to fit into the same orbital as another electron. So therefore you're going to have repulsion between our two electrons in the orbital. So when you have that increased repulsion, that affects your energy in that specific orbital, and that affects the energy of the electron. So remember, as it says here, the repulsion due to a paired electron reduces attraction of the nucleus. So as we were saying here, oxygen has 4 electrons, so therefore there's more repulsion, so therefore there's less reaction, less attraction between the nucleus and the outer electron. So that's very, very important point to consider. So the same with phosphorus and sulfur. Phosphorus is in our third shell, so 3p3. Sulfur is also in the third shell, 3p4. Again, phosphorus, because it's 3p3, you have the singly filled orbitals, which minimizes any repulsion. The s, because it's 3p3, you have to have one of your orbitals having a pair of electrons, whereas the other two could be singly filled. That makes 4. But when you have a fully filled orbital, you're bound to have repulsion, and that would reduce the attraction between the nucleus and the outer electron, which would in turn reduce our ionization energy as well. But as you go across the period, generally your ionization for your first ionization energy increases because you have more protons as you go across the period. So for example, Na has 11 protons, Mg has 12 protons, aluminium has 13 protons, and so on and so on. So the more protons you have in your element, then the more positive that nuclear charge is. As we mentioned as one of our statements or factors affecting the energy of an electron, the nuclear charge, the number of protons in the nucleus. So the more protons in the nucleus that you have, the more ionization energy you require to remove the electron, because there's more attraction between the nucleus and the outer electron. So the more positive protons you add to the nucleus, you're going to have greater difficulty trying to remove the outer electron because there's more attraction between the outer electron and the nucleus. Finally, we're looking at the trend in groups. So the first ionization energy of group 2 elements, so you're going from beryllium to magnesium to calcium to strontium and to barium. So as you can see down the group, we are actually losing shells down the group. So we're going from the we're actually increasing shells, as you go down the group. So because we're adding more shells in, so beryllium has the least amount of shells, barium has the most amount of shells. So as you go down the group, you're increasing your number of shells. So because we're increasing the number of shells, we're getting more shielding as we go down the group, and the outer electrons are getting further from the nucleus as we go down the group. So because the outer electrons are getting further from the nucleus, there's less attraction between our nucleus and the outer electrons. So therefore, less ionization energy is required to remove an electron because of that reduced attraction between the nucleus and the outer electrons as you go down the group. So hopefully that's explained the trends. So the trends down the group, as you can see, as you go down the group, the first ionization energy decreases. As you go across the period, the first ionization energy actually increases, because remember, across a period there's no differences in shells. The only difference is that we have more protons as we go along our period, so that greater nuclear charge. So that's the trends in ionization energies then across a period and down a group. Factors affecting the energy of an electron, we've gone through that. So the orbital, or the subshell, or the set shell, all of them could have different energies regarding them. So referring back to the Orff-Bauer principle, where different subshells have different energies associated with them. The nuclear charge of an atom, the number of protons in the nucleus. The repulsion, we've talked about repulsion, caused by paired electrons in an orbital. So remember, our orbitals need to be singly filled first in order to minimize repulsion. The number of electrons between the outer electrons and the nucleus shielding, and the distance of electrons from nucleus. Again, that is linked heavily to shielding. And then remember, the successive ionization energies, there's a big jump. There's usually a change in shell or subshell. So yeah, we've also mentioned as you go across the successive ionization energies of an element, the ionization energies become larger because it gets more and more difficult to remove an electron. Because once you remove electrons, you start to go closer and closer to the nucleus. Therefore, the attraction builds between our electrons and the nucleus. We also discussed successive ionization energies, which are Al going to Al plus, Al plus going to Al2 plus, Al2 plus going to Al3 plus, Al3 plus going towards Al4 plus. So as you can see, each successive ionization energy starts with the previous reaction. So the second one starts with the product from the previous reaction. So Al plus is a reactant in the second ionization energy, whereas it's the product in the first ionization energy. And the same thing for Al2 plus, it is a reactant in the third ionization energy, but a product in the second ionization energy. So that is the case for successive ionization energies, and as you can see, the more ionization energies you do, the bigger that number gets for ionization energy. Also guys, definition is really, really important, so make sure our definition includes those words in bold. So energy required, 1 mole, and gaseous atoms. So hopefully we learned a lot about ionization energies today. So I hope you're doing well, and we'll continue this within the lesson.